All right, so good afternoon. So some of you have done the lab this morning, and the other half will do the lab on Friday. So the point of the lab was mainly for you to get used to the system and for us to debug any issue. So next week we'll start the real labs, and they'll be assessed. So it'll be 2% for the marks for each lab for the coming weeks. And the lab shouldn't be too hard to do, so try to keep it. You don't have to work for the entire week on the lab. On Monday, I introduced you to the course, and I said that the main focus of the course will be on deep learning. Okay? And because most of you wouldn't have done any machine learning before, we're still going to run for the first few weeks, so about 4 weeks, some general content on machine learning. And the main point of this part of the course is to give you the fundamentals that are interesting for deep learning. Now, machine learning is a very vast domain, and there's millions of different types of methods out there. So we don't want to cover all those. So the things you're going to see in the next few weeks are very, they're selected based on what we think is useful for machine learning, for deep learning. We will have run this course, say, 4 or 5 years ago. The content will have been massively different. The emphasis will be more on support vector machines and so on. But obviously, this is not the case. So we're going to start easy with linear regression. And some of you would have done that. I'm pretty sure all of you would have done that. Has anybody not done it before? No, that's good. So it's going to be a nice and easy introduction, mainly so that we can review some of the elements that are really fundamental to deep learning. Okay, so usually where you start, okay, you have a bunch of data and you want to fit a line. Okay, this is how we start. This is linear regression as you know it. Okay, so all this course you have here, the slides are online, okay, on Blackboard. So I'll try especially during the first few weeks where it's a bit more mathematical, I'll try to just go them through more like pen and paper. I'm recording that and trying to put that on Blackboard as well as we go along so we can review. So hopefully that will work. Okay, so today and tomorrow we'll cover some aspect of linear regression and least squares. Okay, and the two names are equivalent. Okay, so least square is the ancient name for its proper name, and linear regression is more coming from a statistics background. So people in statistics starting to use least squares in the early 20th century, and they use the term linear regression. And actually, it's something we're going to see in a bit more detail towards the end of the course. So least square, if you want, is the first known machine learning technique. Okay? So it's a bit old school, but it's really a powerful machine learning technique. And I would say if you have a problem, even before trying any of the subsequent machine learning technique, you should really just give it a shot with least square. It probably will work. Okay, so kind of don't jump into the big guns of deep learning. Always trying to think, okay, is least square working? So remember in the first course we mentioned there are 3 kind of fields of machine learning. There is supervised and reinforcement learning. And though obviously this belongs to the class of supervised learning. Okay, so by that we mean that you are going to have a bunch of data you have. So let's say you're a web-based company and you have some information about one of your users. Okay, so you have a number of data collected about this user. So typically, the data collected would be, say, username, the age, the weight, the the broader history for the last 10 years, content of all emails, and usual stuff that people have about people. Okay, and some of that data would be continuous value. Okay, so it would be like a real value. So maybe say, for instance, the weight of the person. Okay, and some of it would be more categorical data. Okay, so it would be say, is it female or male, for instance. Okay, so that would be categorical data, and that would be more like a continuous. Now, in least square, we don't really do very well with any other categorical data. Okay, so we do well with stuff like weight, age, things that have a range of numbers, continuous range of numbers. Okay, so in the following, we'll assume that that's the kind of data collected about the person, and basically you have all this information collected about the person. So each of these x1, x2, x3, x4 are called features. Okay. Okay, so features. And I will always call them X. Now, if you come from machine learning, so machine learning is a term coined by more like the computer science community. But if you come from statistics, okay, they'll have different names for it, of course. And but in statistics, you have a much stronger emphasis on convention of notations. Okay, I'll try to stick to the conventions you have in statistics. So I will always say that my observations or the features I collect are called X. Okay, so that's always by definition just say it's X. Okay, and so this is the information I have about the person, and then somehow I want to find a model. So basically a function of these inputs, and they will give me some outcome, and the outcome I always call it y. Okay. And in this case, the outcome is a scalar number. The outcome could be a vector, okay? It could be anything you want. But the problem would be you could recast that problem by having multiple scalars, okay? So we just define it here with the outcome being a scalar. And the outcome is called y as well. And the aim of supervised machine learning is to try to estimate this function f. To have a model for that, train, and to get an approximation for it. Okay. So other notations. Okay. You always say you have p features. Okay. So it's kind of p is the integer used for the number of features you have. Okay. So all this is conventions, of course. If you use different notations, it's all fine, and people will still probably understand you. They just conventions I do, okay? So this is how we start, okay? And so usually you do that for, so the least square, so where least square starts, okay? So that's basically machine learning, supervised machine learning. So you have some data with features collected for each of the observations. And you try to estimate this function f that applied to the data will give you some outcome, okay, whether the person buys your product or not, okay? So in linear regression or in least square, as the name indicates it, we have some assumptions about the model. And we say, well, the model is going to be a linear combination of all these input features, okay? Plus a constant term, which is sometimes called the bias. But that's not that important. It's just called the bias in the deep learning literature, so I'll just mention that here. And your W's are your parameters, okay, your model parameters. Now, in statistics, usually these are called they're called betas usually. Okay, so usually they use a Greek letter beta for denoting these parameters. The reason why I mentioned in the slides W, it's because, once again, in the deep learning community, people just tend to use more W. So I just stick with W, and this is what you have. Okay, but just be aware that there's a number of conventions on how things are called. Okay, so that's pretty simple. So we have a linear model. That's our approximation of how your data should be. And obviously, we want to estimate the parameters, W's, that would fit that model. Okay. So, so if you come back to quickly to that example here, so we collected the information, the feature we collected about the person is the height, and we want to infer the weights. Okay. So on the x-axis we have the input feature, and the y-axis here we have the outcome. And we're trying to find a straight line that will go through that data, so we can say, make a prediction. So here the prediction is that the weight is the height times centimeter times 0.9722 minus 99.5. Okay, so you have a nice prediction on your data. Okay, so obviously it doesn't work all the time, but it's kind of the model you have at that point. Okay, so let's look at what we have, okay? So we're going to collect data for a number of people, and so we're going to have a number of outcomes. So I'd say, outcome number one is, so W0 plus W1. And here I'm going to index the features a bit differently, because now I need to index for the client number, okay? So I'm going to index it first on the first sub-index will be the number, the observation number if you want. So I say it's x1 and it's a feature 1 of that guy. And then I keep on going, and then I have WP of x1. So we're still talking about the first individual. And then we have here the PS feature, okay? And then you keep on going like that, so you can go y2. So you still use the same weight, okay? And the only thing that changes is basically the entry you have, okay? And by convention, you stop at n observations, okay? So you say you have n observations. Sorry, 1 x and 1 plus WP of x and p. Okay? So you have n equations, okay? So n is a number of observations you have, okay? P is a number of features you have. Okay, so keep that in mind. N is the number of observations, P number of features. Okay? So you have basically n equations, okay, with P unknowns, okay? And obviously, we've seen that in the graph, the model is not perfect. You're not going to model things, spot on all the time, so you have to account for some error term, okay, and or noise. And so here we have the noise expressed as this epsilon. Okay, I just got epsilon could be any term here. Okay, so this is really what you have. You have n equations. Your model is expressing these W's, and the x contains all the features about all the observations you have, and you have this error term epsilon. Okay. At this point, what you want to do is to somehow find the W's that will minimize the error. Okay, makes sense. You just want, you're interested in W's, and you just want to try to minimize the error. Obviously, the problem you have is that the error is really a vector. Okay, and you cannot really say whether your a set of W is better than another one. If what you have to compare is vectors. I mean, you cannot rank vectors very well. Okay, you cannot say a vector of error is better than another one. That you can do. Okay. So what you need to do is somehow aggregate all these epsilons into one function, into one error term. Okay. And this error term is called the loss function, or the objective function, or the error function. It has many names. But in our case, I'll just do that here. What we say is we have an error function of W. Okay. So here I use the matrix notation, so it's an error of all your W's. Okay. So we could say. Okay, which is equal to, and in least square, okay, what we choose is to do the mean square. Okay, so in our case, it'll be something like 1 over n over the sum of going through all your observations of basically what's your predicted outputs. Okay, so what's your predicted output according to the model, minus what you actually observed, and you square it. Okay? So this is called the mean square error of the model. The y hat, sorry, I'll just write it here, is basically what your predicted value is for your input features according to your parameters. Okay? Okay, so basically for every single one of your input, your observations, okay, you're going to look at the features, apply your model parameters. Okay, you have a model and you plug in your model parameters, and you get, if you remove that, that's your prediction here, and what you get here is an expected value for y. Okay, and you say, right, I want to check whether my expected value actually matches the real value, which is the one I know I have. Okay. And then you just say, well, the overall error is this average of all the squared error. By the way, the fact you have 1 over, like the fact it's the average or the mean doesn't really matter. It could have just been the sum of the square. Like, it really depends on what you read. The optimization doesn't matter what you have. The 1 over n here, it has no impact. Okay, so we've defined everything. So we have defined the features, we have defined the model parameters, W's, we have defined the outcomes, Y, and we realize, okay, we need to optimize for the error, and we say the error function needs, we need to define an error function, which is just a simple number we can compare against to know whether one set of W is better than another one. And we chose this error function, which is a least square. Okay. It's important to realize that there's plenty of different choices for error functions you could have applied. Okay. So we could, for instance, have used the mean absolute error. Okay. So the error function, this one for the, it's called the MAD actually. So of my parameters, then would have been something like that. So sum of all my samples of this time the absolute difference between my prediction and my the actual outcome I have. Okay. This is very interesting. Okay, and this called this is links to something called L1 optimization. But this is not the scope of this course, and this leads to totally different mathematics. Okay, so when you do least square, and you have it in the title, okay, you really look at the loss function here. Okay, and the loss function is the average of the square differences you have. Okay, so this is a very important point. Okay, so so let's try to optimize that. Okay, so this is something not thin. Okay, so I'll just move. So we come back. So we have our energy or loss function. I'll just right here post. By the way, loss function is a term mainly used in machine learning. Okay, in statistics, people will use different terminology for that. Like there's lots of name for it. Okay, I'll just stick with loss function because this is what you'll see if you read deep learning literature. So I'll write this again. And I just expand it according to our models. So that is what we want to optimize. And now you have a function of multiple parameters, and you want to find the minimum of that function. And we know from calculus that you will get the minimum when you take when all the partial derivative are null. Okay, so when you take the partial derivative of that expression according to 0 is null, and so on and so forth for all the parameters. Okay, something you've seen many times. It's just your error function. If you're in 1D, okay, would be something like this, okay, and that would be, say, if you only had one parameter, okay, and then you say, well, here, the function reaches a minimum. If it's smooth enough, then you can compute the gradient, and the derivative will be just null at the point. Okay, it has to be null. Okay, so all you need to do then is, so it applies for p dimension as well, and so all we need to do now is to compute this partial derivative and express them, okay? So let's do that. So I'm just going to write it for one feature, so I just look at the partial derivative of the loss function according to, let's say, wk. Okay, so just take one of in particular. So the derivative operator, okay, is linear in that case. So you have still a sum here, and sum goes here, and you just need to be able to compute the partial derivative of this expression. Sorry. Okay, so there's only one wk in that expression here, okay? And so remember the derivative for polynomial of order 2 is quite straightforward. What you get here is basically the coefficient of wk, and the coefficient of wk here has to be xik, okay? And then you have these guys at power n-1, so in this case, just the term itself. And times 2, okay? All right, makes sense? Taking baby steps here. I see some frowning. All right, remember, if you have if you take the derivative, so just forget your ND, okay? If you take the derivative of, say, ax plus b squared, what you get is 2a times ax plus b. All right, make sense? Yeah?
Can you explain again why we're taking the derivative?
So, so we have a function of this many parameters, and this function has to reach a minimum. Okay, so we want to find what is what are the values of all w's at the minimum. Okay, and the classic approach to find the minimum of a function, the argument that will minimize a function, is to say, well, when you reach the minimum, we know that the derivatives, all the partial derivatives, have to be 0. Okay, and I'll try to give an example here. Okay, so let's say you have a function with only one argument, w0. At some point, it reaches the minimum. Okay, and the minimum here, it has to go down and then go up again. And if you look here, the slope has to be, it has to be horizontal. So at that point, you have the derivative of that guy is 0. Okay. So we use the same argument for all the dimensions. Okay, so it turns out that you can say, you have a function of many arguments, but if you want to reach the minimum of that function, this function is, if you can differentiate it, then we know at the minimum of that function that the derivative respect to all of the parameters has to be 0, because otherwise it wouldn't be a minimum. Otherwise, you could nudge a bit in one direction and get a bit lower. All right? It's a classic trick, like maybe you didn't do physics and so on, but like that's what you do all the time. When you have a function, you want to find the minimum, you look at the gradient equals 0. Okay, so coming back, okay? So we have this equation, okay? We have the partial differential equation, the partial derivative of the loss function. That's the expression for it. And we know it's 0. Okay? All right, that's a big one. So it means that, try to put that here. Basically, for each of the w's you have, okay, you're going to have an equation that, an expression here that equals 0. Okay, so the first one, I'll just write it for you. So I'll just put the 2 here in front. Okay, so 2 over n of sum of I equals 1 to n. And then just going to write it this way. And then you go down and you have something here, 2 over n, sum I equals 1, n of I. And here you have it's IP, W0 plus WP. Okay? So basically here, with our conventional notations, we have P plus 1 equations. Okay. Right. So we can reorganize things a tiny bit, okay? And I'm just going to extract all the parameters on its own and write the coefficient in front of it, okay? So the first line, we have W, 0, and you have 2 over n of the sum I1 to n of 0 plus W1 of 2 2 over n of sum of xi0, xi1 plus wp 2 over n same sum I0 xi p, and then you have here, I just put it on the other side, yi times, sorry, that's badly prepared here, 2 over n of the xi0. All right, so this goes here. Okay. And you can go down, and you have here, try to do so. Okay. These equations are written in the slide. Okay. So if you take the 2 over n on both sides, I'll just show you briefly what it gives you. Sorry. Gives you something like that. Okay. So it's just another way of, a cleaner way of presenting it. So you have a system of equations. You have p plus 1 equations. You have your w's everywhere, okay? And you have the coefficient in front of the w's that depends on your data features, okay? The features. And at this point, you can solve that, and it's all fine. And these are called basically the normal equations. And use any kind of linear algebra software, and you're good to go. Okay, so this is how we got the line here. The coefficients were estimated using that technique. Okay, so I have a linear system of equations that relates my weights to my features, and I'm able to invert the system. Sorry, going back here, invert the system, and it's all fine. Okay. So this is a kind of painful way of doing the calculus, okay? So usually that's kind of the way you come back to, because this is the way you're the most comfortable with, okay? It's just summations, differentiations, and it's not that complicated. You can do it. You just have to be careful with all the indices, but you're fine, okay? And you've seen that before.